The last thing we need to talk about in this section deals with complex eigenvalues. So when we talk about complex numbers in general, we're talking about numbers that can be written in the form a plus bi. Our textbook's using alpha and beta instead of a's and b's. We know that complex numbers always come in pairs. We saw that back in 171 when we were trying to find roots of a quadratic that may have complex roots. They always come in pairs. We found those using the quadratic formula. Same thing is going to be true here. Complex numbers in general come in pairs if we're solving some kind of equation. So in this case, what we're talking about is solving a system of differential equations, and we need eigenvalues and eigenvectors to do that. So if we find eigenvalues, those eigenvalues, if they're complex, will always come in pairs. And it turns out that they're going to be complex conjugates of each other. And the same thing is going to be true for the eigenvectors. If we have lambda 1, let's say our lambda 1 was 1 plus 2i. Then our lambda 2 would actually be the complex conjugate of lambda 1, which would be 1 minus 2i. So then it will also turn out that the eigenvectors for lambda 1 and lambda 2 will actually be complex conjugates of each other. So let's look at an example. But before we do that, let's talk about what the real solutions are going to look like. So if we find these complex eigenvalues and eigenvectors, and they're using lambda 1 for the first one, and they're calling lambda 2 the conjugate of lambda 1. And remember, the conjugate notation uses that line above. So then K1 would be the eigenvector associated with lambda 1. The conjugate would be the eigenvector associated with the conjugate of lambda 1. So these guys are coming in pairs. And then the format for x1 and x2 can be written this way. So B1 and B2 are going to be column vectors. Our beta is the number that's attached to the I component. Our alpha is the number that's by itself. And so we're really just taking everything and we're plugging it into this. When they talk about B1 and B2, B1 is really looking at that eigenvector and dissecting it into the real part and the imaginary part. B1 happens to be the real part, B2 is the imaginary part. So it's really important just to make sure we have all the parts labeled so that everything's easy for us to figure out. We're actually also going to use Wolfram Alpha to help us solve these matrices and find the RREF when we find the determinant of A minus lambda I. If you took linear algebra, you could do row reductions to find that also. That's a fun thing to do on a Saturday night when you're bored. But I'm going to show you how to use technology to do that. You could also solve the system of equations, using substitution or elimination. So there's multiple ways to do it. Your calculator, if you have a TI 83 or 84, does not have the capability of using imaginary numbers inside of the built-in matrix operators for those particular calculators. I think the TI 89 may be able to do it, but I'm not quite sure. I haven't played with it enough to do that. So let's look at an example. We have a system of differential equations. It's written in matrix form. And we also have initial conditions, and that's given here. So this one's going to be fun because we will be able to figure out what C1 and C2 are. So all the problems are going to start the same way. We need to find the determinant of A minus lambda I. And then we need to set that guy equal to 0. So if we take our A matrix, which is 2, 8, -1, -2, and we subtract lambda times the identity for a 2 by 2, which is 1, 0, 0, 1, then we are going to get 2 minus lambda, 8, -1, and -2 minus lambda. So we want to know, where is this determinant equal to 0? So to find the determinant of a 2 by 2 matrix, we're going to multiply down the diagonal, going left to right, subtract, and then multiply down the diagonal from right to left. And then we want to set that equal to 0. If we multiply out here, we have -4 minus 2 lambda plus 2 lambda plus 8 is equal to 0. Plus lambda squared plus 8 is equal to 0. So we have lambda squared plus 4 is equal to 0. So lambda is equal to the square root of -4, which is going to give us imaginary numbers. Okay, so notice these are coming in complex pairs here. So now we need to find the eigenvectors. So I'm going to use lambda equals 2i. So if we were to take 2i and substitute it into this matrix up here, this guy, we are going to get that. We're going to put this with a 0, 0, and now we want to do RREF. So this is where we want to switch over to Wolfram.